Hi, welcome to this lecture. So for today, we will be discussing conjugate beam method. So this method is the third method under the geometric methods of how we solve the deflection and slope of a beam in structural analysis. Okay, so conjugate beam method is a method uh, to compute beam and slope and deflection, but it's different from moment area method and double integration method because it's much more simpler. Simpler in a manner that we will know in the next slides. So to introduce, this method is a technique that uses an imaginary or conjugate beam to determine the slope and deflection of a real beam. So as mentioned here, in this method, the loading of the conjugate beam is composed of the M over EI diagram. So this is the M over EI diagram of the real beam, and the shear and moment in the conjugate beam correspond to the slope and deflection of the beam, of the real beam. So conjugate beam method is a way of computing the slope and deflection but using statics, ano? So, sabi dito, we create a fictitious beam na tinatawag nating conjugate beam. In this conjugate beam, meron siyang same length of the real beam, okay? Pero dito, the loaded or the bending moment diagram divided by deflectional rigidity or yung M over EI diagram of the real beam is loaded dun sa fictitious beam natin, which is a conjugate beam natin. And then we apply yung rules ng statics to solve for the shear and moment of that fictitious beam. Okay? But we also need to determine yung behavior ng support to sa fictitious beam natin kasi we need to predict or to satisfy two theorems in order to accept that the fictitious beam or the shear moment diagram of the fictitious beam will correspond dun sa slope and deflection talaga nung real beam natin. Okay? So, why use this method? So, this method kasi is more familiar to us kasi we are more trained to calculate for the shear and moment of a given beam. No? So, it is more easier and more intuitive rather than integrating or moment area na nakabase tayo doon sa elastic curve or doon sa deviation ng tangent ng mga points natin from a tangent line. Okay? So, we have two fundamental theorems for the conjugate beam method. Number one is the shear diagram of the fictitious beam of the conjugate beam is actually equal dun sa slope daw. Okay, so the slope at any section of the real beam is equal to the shear at the corresponding section of the conjugate beam. So as you can see here, we have here yung fictitious beam natin. So you can see yung loading niya, yung M over EI na, no? So if you will see na M over EI, this is the conjugate beam na already. So once we get yung value nung kanyang shear diagram, okay, ito yung shear diagram niya. So kasi may apostrophe to um, say na ito yung sa fictitious beam natin, ano? And then this is our original beam. And then once we get, di ba, yung derivative of our original loading, nakukuha natin yung ating slope, ano? So, ganito kasi yan. So, we have our, halimbawa, from our previous discussion, when we have our loading, okay, or yung y natin, once we get yung derivative niya, yung y prime natin, okay, that is actually our slope, ano, yung d theta over dx natin. Okay? So, paano natin i-accept na yung shear o yung shear na makukuha natin sa fictitious beam natin is equivalent dun sa mismong slope ng ating original beam, ano? So, From our curvature equation, again, y double prime is equals to m over ei as we derived before. Once we integrate this, makukuha natin si slope, ano? M over ei. Okay? And then, si slope can be represented as d theta over dx, so mei. Okay? Or, we can represent as d theta equals to m over ei dx. Okay? Performing integration, we have si theta, no? Kaya, ano tayong first integration is equals dito sa equation na to. Okay? Then we also have from our moment equation before, for shear and moment equation, if you would like to check if our shear equation is correct, we take the derivative of the shear with respect to x and then equate it or check it if it's equal dun sa applied loading natin. Okay, so when we perform this, dv is equals to the loading times dx, integrate it, we have v is equals to w dx. Okay, so as you can see here, we are performing the same manner nung ginagawa natin. So dito, sa fictitious, kinuha natin uh, yung kanyang derivative, makukuha natin yung kanyang slope, which is this one. Yung sa sa original real beam natin, yung um, derivative naman nung diagram natin will be equals to sa loading natin. So in a manner, we can equate these two, ano? So kaya sabi natin, itong slope natin o yung shear na makukuha natin from the fictitious, okay? Equal daw yan dun sa slope natin. So this is the first um, theorem is all about, ano? So it's saying na yung conjugate beam natin, yung shear niya is equals to sa rotation of the real beam. So ito yung pinaka first concept natin sa kanya. Okay? Whatever is the value of the shear equal siya sa rotation natin. Okay? And then for theorem 2, any value ng moment or whatever is the value of the moment in the conjugate beam, ito no, value sa conjugate beam will be equals dun sa deflection daw natin. Okay? So, same analogy siya nung before. So, di ba, once um, we have our curvature equation, okay, d squared y over dx squared is equals to m over ei. This is our curvature equation. And then, once we perform this, para makuha si y, o yung deflection natin, okay? So, ginagawa natin yung double integration, ano? Kaya meron tayong y is equals to double integration ng m over ei dx, tapos ito naka-dx pa yan dito. Okay? Para makuha yung mismong deflection natin. Ngayon, for moment, ganun din. So, kung gusto mong makuha yung moment, okay? So, di ba, we have kanina, si dv over dx ay equals sa loading natin. Okay? But, the derivative of dv over dx, okay? So, di ba we have the derivative ng moment with respect to x ay equals sa v. So, if we take the derivative of b here, it means that w, we can take the second derivative of the moment equal siya dun sa loading natin. So, dito, pwede natin perform ulit yung yan. So, w dx squared. Pag perform natin, makukuha lang din natin is moment is equals to integration o integral ng loading dx dx. And as you can see, it's the same manner nitong sa deflection natin. So, pag inequate mo, yung moment ay equals dun sa deflection natin. Moment is equals dun sa deflection. Okay? Or in simpler terms, whatever is the moment value in the conjugate beam, okay, that is the value of the deflection. Okay? So, ano lang yung twist natin? So the twist here is that whenever using a conjugate beam method o yung fictitious beam natin, we need to also convert yung mismo support condition natin. Ano? So, kaya we have guides to consider. So, since si real is yung slope and deflection natin, si conjugate is dun sa shear and moment natin. Let's say we have an pin or a roller. So, alam natin pin and roller cannot deflect or wala siyang movement sa vertical direction, so hindi siya pwede mag-deform. Pero pwede siya mag-rotate. Pwede siya magka meron ng movement dito sa rotation natin. So, kaya dito. So, equivalent again ng, ng slope sa real ay equal sa shear and then ang ating deflection ay equal sa moment. So, kung ito ang inaalaw natin na magkameron ng slope, ibig sabihin, the conjugate beam, inaalaw natin na magkameron ng shear. And ang shear dito, of course, is yung vertical or yung transverse loading natin from the support, which is also the same pin na wala siyang moment, no? Okay? And then, same with the roller. Okay? For fix, we cannot have any rotation or movement from any direction. Kaya, para mawala ng shear at ng moment, kailangan free end lang siya. And kapag free end siya dito, ibig sabihin pwede siya mag-rotate, pwede siya mag-deflect. Kailangan magkameron ka ng value ng shear and moment para magkameron ka ng shear, para magkameron ka ng deflection tsaka slope. Okay? And then here are some more rules to follow. Okay? For continuous, for internal roller, if you have internal roller, just change it into uh, a roller, no? And kapag internal, pag meron ka mang internal hinge, okay? So just change it. So internal roller, internal pin. So let's rewrite this. Pag meron kayong internal roller or pin, gawin nyo na lang sa conjugate niya, may hinge kayo. And vice versa, kapag meron kang hinge, gawin mong internal roller. Okay? Medyo, ano pa kasi to confusing pa tong other na nakalagay dito. Okay? Yeah. So let's have the procedure. So what we need to do is determine yung bending moment diagram ng real beam. And then after that, divide natin yung moment diagram by the flexural rigidity. So we need to do this kasi some beams don't have the same value of inertia. Ano, or iba yung I niya or elasticity niya. So you need to check, no? Check it always. And then define daw natin yung conjugate beam. It means we convert yung real beam natin into conjugate beam. And then apply natin yung nakuha natin sa number 2. And then analyze natin yung conjugate beam, meaning get the shear moment diagram, and then interpret the result depending on the point in question. Okay, so let's have our first example. So this is the same example we did for moment area to show yung comparison niya, no? So for this overhanging beam, we need to find the slope and deflection at B. So at the free end, ano? So to calculate this, we need to get the reaction first at the support. So we know that at this section, we need P there to negate yung P na applied at B. And then this loading will cause a clockwise rotation or movement towards the support. So to negate that, the support should um, exert the opposite direction or counterclockwise direction. Okay, and then we perform the shear and moment diagram niya. Okay, for the shear, we have the shear. So we have P, and then all throughout the length, there's no disruption sa Y natin or sa vertical. So P pababa. So this will yield 0. So this will be our shear diagram with an area of P times L. Okay, so we get the area so that in plotting yung moment diagram, we will just refer dun sa area. So for the moment, at first we will be having a counterclockwise moment, so that is um, going downwards, so negative PL, and then add the area of the shear diagram. So negative PL plus PL, that will be yielding a zero number. So from a first degree curve, so we're not in second degree, which is a linear or straight line. Okay, and this is its area. So area niya would be 1/2 negative PL, and then since EI is constant, we just need to divide it by EI, same shape, multiplied by the length. So answer will be negative PL squared over 2EI for the area of the triangle. Now, we need to get the value of the slope. So again, let's check our step. We got the moment diagram. We divided it by EI. Next step is to define the conjugate beam. Okay, so looking at the first support, the left support, so A natin, that is a fix. So from our diagram, if it's fixed in the real beam, gagawin lang natin siyang free on the other end. Okay? So, sabihin, wala na siyang support dito sa conjugate natin. And then, uh, kabaliktaran naman niya, from free dito, no? So, point B natin, when we look at the diagram, from free, magiging naman daw siyang fix. So, we just need to convert this one into a fix. Yeah, so this is our conjugate beam, our fictitious beam. Okay, and then the loading will be whatever is the moment diagram. So the moment diagram is a triangular load with intensity negative PL over EI. Okay, so this is our point P. So to get the shear moment of this beam, again, reaction. So we have our ECL here. So wrong direction. Okay, so that is 1/2 of PL over EI times L. So that is negative PL squared over 2EI. And then it will be resisted by this shear. So let's call it By. And then the moment will be resisted by moment at B. Okay. So for the shear, so summation of for the shear, this is the shear at B. Okay. So summation of forces y is equals to 0. So we have negative PL squared over 2EI, then VB. So VB is equals to negative PL squared over 2EI. Okay? And for the moment, summation of moment at B is equals to 0. So negative here on the other side. So this is MB, not negative. And here we have negative PL squared over 2EI multiplied by 2/3 of the length. So MB will be equals to negative PL cubed over 3EI, which is the answer. So it means this moment is equivalent to the deflection at that end, and then this is equivalent to the slope at that end. Okay, so if you check the solution for the moment area video, you will see that it would be the same answer. Okay, next, let's try another example with values this time. So an overhanging beam with 6 kilonewton at the free end and then moment at center. So first is to get the support reaction. We have 6 here. Then we have moment that will be negating an 18 and 6 times 6, so 36. So that is equal to 54. Okay, kilonewton and then kilonewton meter. And then we have our shear diagram. Okay, for shear diagram, it will be like this. So we have 6 here, and then 6 all throughout the length, then 6 down will yield 0. That is our shear diagram with an area. So let's try to divide this shape to 2. So this will be 18 kilonewton meter, and this will also be 18 kilonewton meter. The next, plot the 54 downwards, so negative 54. Okay, and then next is the presence of this loading. So from negative 54 plus 18, that will yield negative 36. And then because of the clockwise rotation of the moment at center will be negative 18, and then from here it will be 0. Okay, so our moment diagram is a trapezoidal at segment A to B and triangular at segment B to the free end. Okay, so EI is still constant, so just divide this by EI. We should be fine. Okay, then our conjugate beam. So for the conjugate again at A, that will be a a free end, and then at the end that will be a fixed end. And still at center we have 18, 3, 3. Then we have 6 here. Okay, so for the shear here at C, let's call it C, is negative 6. Okay, find the deflection at C. Okay, so slope at B, we need slope at B. So we need the shear diagram for B. Okay, so if you cut it there, okay, slope at B. Okay. Then this will be our support reaction. I'll finish this one first. This should be 18 also. Okay, so after that we plot the shear moment diagram of the conjugate beam. For shear, we have no shear at the first 2 points, but here so this is not negative, it should be 6. Okay, we need to do is so we are okay, I know my mistake now, no? So yung sa conjugate natin, mali yung loading natin. It should be the moment diagram already. We don't need this loading here. And wait. Okay, so let's redo this. So this is point A, point B, and point C. And the loading now is a trapezoidal here and a So 54, negative 36 EI, then negative 18 EI. Okay, so to get the ECL of this, I'll divide it into two. Okay, so these are all uh, negative, so downwards. Okay, so the ECL would be this way and this way. So first ECL would be the area of the triangle. So 1/2 negative 54 times 3, that is negative 81. And then the area of the other triangle, this one, the smaller one, 0.5 negative 36 times 3, that is negative 54. And then the area of this triangle, so that is 0.5 of negative 18 times 3 is negative 27. So again, don't forget that all of these values are all um, with flexural rigidity at the denominator. Okay, so we need the deflection at C, so we need moment at C. So we'll just need to get the moment at C. Okay, so summation of moment C is equals to 0. So just rotate all forces. So we have negative 81. So let's do the distances. Okay. So this distance will be how much? So this is 2/3 of 3 plus 3 is equals to 5.0. This one would be 1/3 of 3 plus 3. This is 4.0. And this will be 2/3 of 3, which is 2.0. Okay, so negative 81 over EI times 5. And then we have negative 54 over EI times 4. Then negative 27 over EI times 2. Okay, and then we have moment at C. Moment at C would be negative 81 times 5, 54 times 4, 7 times 2. So that is negative 65 over EI. Unit is kilonewton meter cube. That is also equals to our slope. Okay. So to get the letter B, for letter B, we'll just do the same thing. But for B, for the slope at B, we just need the slope. So we cut the section here at this section at B. So we imagine that that is what is left behind. So let's have that here. This is the cut. Okay. These are the value of the ACL of the true triangles of the trapezoid. And then we need the shear at B. Okay. So summation of forces Y is equals to 0. VB is equals to negative 81 EI minus 54 EI. 81 plus 54. That is negative 135 over EI kilonewton meter squared, or that is equivalent to the slope. Okay, so much simpler. Once you get the hang of it, I think you will be able to do it more uh, easily, or faster. Then our last example for the area moment, and we will also calculate it here. So it's the same, but right now we have the values of E and I, so that's good. So for our support reaction, we have 25 kilonewton, and then we have here 25 times 6, that is 150 kilonewton meter. Okay, and then we construct our shear and moment diagram. Okay, for the shear, so we have here 25, and then 25 at center, that will yield to 0, and then the rest will be 0. So this is 25 times 6, so this is 150 kilonewton meter, the area of that shape. And then we have for moment, okay, for moment we will be moving downward first for negative 150 counterclockwise, and then plus the area of the shear diagram. So it will be 0, and this will be a linear shape. So area of this is 1/2 negative 150 times 6. So negative 450 over, don't forget EI. Okay, so what we need is the slope at free end. So that is theta C, delta C, and deflection at midspan, so delta B. Okay, so let's create the conjugate beam. So free, then fixed support, then A, this is B, and C. Then we'll load the moment diagram. Okay, so this is negative 150 over EI. So its ACL is negative 450 over EI, or the area of the triangle. And then from the support, we can get the shear, okay, and then the moment. For shear, that's AC summation of Fy. So VB is equals to negative 450. That is kilonewton meter squared over. So let's put it here. So we need to convert the kilonewton into 1000 Newton. And then the meter, we need to convert into 1000 millimeter. 1 meter, 1000 millimeter. But since this is in squared, so this should be in squared also. And then over, we have 200,000 times 10 to the 3. Megapascal could be taken as Newton per mm squared. And then we have 60 times 10 to the 6 mm to the 4. So when performed, we cancel mm squared. So we still have 2 here. Cancel here, here, here. And then there will be 1 squared, and then another moment here at the uh, denominator. So no unit will be left. So VB is actually a radian quantity, or the unit is in radian. The answer is negative 0.0375 radians, or that is negative 2.149 degrees. Okay. Then for the moment, so this answer is for theta C. So next, so let's have the moment. So this is already duplicated. So for moment, summation of moment at C is equals to 0. So we have 450 over EI negative times, this is how much? This is 2/3 of 3. This 1.0 plus 3, that is 4. This times 4, this is MB. So negative 450 times 4 meters. This is kilonewton um, meter square, okay, over EI. So this would be 1,000 to the fourth. So just additional 1,000. 200 times 10 to the 3. And then this is 60 times 10 to the 6. So MB is equals to negative 450, 1,000 to the fourth, over 200 times 10 to the 3, 60 times 6. So that is 37.5 times 4, negative 150. Okay, this is in moment, so slope. So this is in, rather deflection in. Okay, next is for the deflection at midspan B. Deflection at midspan B, so let's duplicate it again here. So we need at B. So we imagine we cut the section at that location at B. Then we get the deflection, so we just need the moment, the resisting moment at measure the moment at B is equals to 0. So that is 450. So this is MB negative 450 over EI times 2/3 of 3, that is 2. Negative 900 over EI. So times performing the same calculation as the previous two. Negative 900 times 1,000 to the fourth. 200,000 times 60 times 10 to the 6. Moment at P. So 450. So we go back here. Where does this value come from? Okay. Mali yung value ko, ano? So, ito is not plus 3. So, plus 1 plus 6. Huh? So, this is also not 1. It should be 2. 2/3 of. Okay, so 6. So, multiply it by 6. What is 6? 6. So, this should be 8. 1,000 raised to 4. 200,000, 60. negative 300. So 0.5 times 150 times 6 is negative 450 times 6. So uh, wrong distance again. So this should be 2/3 of 6 plus 6 equals to 10. So this should be C. Okay. Sorry for the wrong annotation. Ano. C, 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 C. Okay. And then this should be 10. Okay, negative 450, 10, 1,000 raised to 4, 200,000, 60 million. Okay, this is correct. 300, negative 375 millimeters. And then for this case, so same procedure, but right now, this distance would be 2/3 of 6, or that is 4.0. This is 4, that is 18,000. Negative 18, 1,800, not 18,000. 1,800 raised to 4, divide 200 times 60 million. Okay, that is negative 150 mm. So that is equals to delta V. Okay, yeah, so these are our answers. Okay, so you can see much friendly yung calculation niya kasi we are more used to solving it using statics, yung shear and moment diagram natin. So medyo convenient siya for us. All right? So okay. So that ends our lecture for conjugate beam method. So if you want to know the other methods, geometric methods, so I have a video for the area moment and also, or the moment area, and then also for the double integration method. And then also I do have a discussion for the energy method, which is the virtual work method. So see you guys again in the next video. Thank you.